Hello everyone, my name is Marco Scaletta and I'm a PhD student at the Software Engineering group of the TU Darmstadt, and today I'm going to present a delta-based verification for software product families. What we want to address is the verification of software product lines that are implemented with the delta-oriented programming approach. With this approach, we can apply deltas that are modification to a core variant, and in this way we're able to generate variants that are our products. The problem of this approach is that the implementation of a method can change. So when we call it, we don't know which is the version of that method because it has many different versions. So when we call it, we don't know which is its actual version, and in this way we are not really able to verify its behavior or verify the behavior of method that calls it. The idea is to apply the contrast-based approach in order to perform the verification of software product lines. With this approach, we specify the behavior of a method by precondition, postcondition, and a frame. When the precondition of a method is true, then applying, executing the method ensures that the postcondition will hold. And also we have a restriction that only the variables that are included in the frame can be assigned by that method. For example, here we have a method M1 that calls method M, and we can compose this to contract in order to have the verification of method 1 only relying on the contract of method M. The problem is that with the delta-oriented programming, since we don't know which is the version, the actual version of a method, because it has several versions, then we cannot really apply this contract-based approach, but we can apply it with the product-based verification. That means that we consider each possible version of a method. The problem of this approach is that the complexity is exponential because we are basically generating each possible variance, and this is a too expensive approach. Therefore, we are trying to overcome this complexity and these expensive costs. A possible alternative to the product-based verification is the Liskov substitution principle for delta-oriented programming. With this principle, we are enforcing a relation between contracts that is called more general than, such that if a method satisfies a contract, it also satisfies each more general contract. In this way, if we enforce a relation, an order between contracts, such that each contract of a method is more specific if it's a subsequent version of that method, then we are able to apply the compositional verification, and in this way we are not obliged anymore to generate each variance. This is because we can, when we call a method, only consider the most general version of its contract. In this way, the complexity is now polynomial instead of exponential. Now a problem arises since each version of a method have the same most general behavior. That means that deltas do not really modify the behavior of methods. So the challenge now is to go beyond the Liskov restrictions, and with the idea to not increase the cost. And the solution we propose is so-called delta-based verification, because we are able to verify deltas in isolation, and the main idea is to represent original calls as abstract programs, since we want to represent a set of programs instead having to consider each possible version of method. We consider the set of possible versions. Then we have to understand how to deal with abstract programs, and because, for example, if we have a fully concrete update, it's clear what is the value of x in the state sigma 2. But if we have an abstract program executed in sigma 1, then we don't know which are the values of x and y, actually we know that row 1 is not a state, but is a set of states, because it contains each possible configuration of x and y. And the idea is that if we constrain the frame or the assignable clause of the abstract program's queue, then we are able to say, for example, that all the state in row 2 have as value of x 0. How can we verify this property? Well, we can do that with abstract execution. We are able to prove universal behavioral properties, for example, that after executing q with the frame that doesn't contain x, we have that the new value of x is equal to the old one. The idea now is to use abstract execution to represent original calls as abstract statement. In this way, we have to deal with a single abstract program instead of a set of methods that are represented by the original call. Doing so, we are also able to go beyond Liskov, because with the Liskov, we are not allowed to include new fields inside the frame of a modified method. The contract you see here can be verified with abstract execution, and we can use the keyword old field L in order to refer in an abstract way to the behavior of original regarding to the value of a field. And the idea is that this contract cannot be invalidated by Delta applications, and in order to have a more general schemata, then we have to introduce the so-called behavior preserving methods. A behavior preserving method is a method whose behavior cannot be modified or affected by Delta application. And for example, if it's a modified method, then it has to fulfill Liskov, or if it's not modified, then it of course cannot be changed by deltas. But also we cannot have calls to non-behavior preserving methods in these methods, otherwise a delta might in an indirect way change the behavior of these methods. Here is an example, and we can see methods satisfying Liskov because the ensures on the right implies the ensures on the left. So with this modification, we have the contract on the right is more specific than the contract on the left. But we cannot really do that with, for example, method M4, because the ensures in both cases are too specific already. So what do we have? We have that methods that are not modified or methods that satisfy Liskov are behavior preserving, and the red one, method that do not satisfy Liskov but are modify or call non-behavior preserving method, are non-behavior preserving. We can also define a BP sequence as a sequence of statements that do not call non-behavior preserving method. Now we have the core of our approach, that is the shallow single original normal form. In this form, we have that there are two BP sequences that are wrapping the original call. In this way, we have that the behavior of this method cannot be changed by Delta's application in an indirect way. It's possible to refactor to the normal form even methods that are not in the normal form. For example, in this case, we have that there are two original calls instead of one, and we are able to refactor it in order to have the BP sequence S1 and the BP sequence S2 wrapping the original call. Also, we use abstract execution to prove the correctness of this refactoring. And now we introduce the more general schemata so that we can have a more general approach to verification of Delta-oriented programming software product lines. The idea is to introduce this principle, so-called change all behavior principle, that enforce a normal form over the body of modifications so that the original is wrapped inside two BP sequences so that we can represent the original model, the original, as an abstract statement, and then we don't have to deal with indirect changes of this method. So when we verify this method with abstract execution, we don't have to re-verify it if a delta is applied to our software product line. The idea is that the BP sequence S1 can only assign newly added fields so that we don't affect the behavior of original. But we have that sigma. The BP sequence S2 can do whatever, because we can apply, for example, assignment to previous fields or newly added fields, and in this way we are able to change the old behavior of original. With this theorem, we guarantee that our approach is correct. The main idea is that we can enforce, we can apply a delta-based verification and verifying isolation each delta, because when we verify a contract, we don't have to re-verify it if we apply new deltas, or we can apply a delta-based verification and verify in isolation each delta, and application of delta does not affect the behavior of a method that are previously contract that are previously proved to be correct. And doing so, since each contract has to be proven once and we don't generate any variant, the complexity of our approach is polynomial. So we have the same complexity as Liskov, and we go beyond his restriction because we are able to override previous behavior, to change previous behavior. In order to evaluate our approach, we wanted to know if it's expressive enough to specify and verify existing software product lines, and also which are its performance. For the first point, we consider two widely used software product lines: bank account, that is a software product line for managing a bank account with withdrawn fees and so on, and mine pump SPL, that is a product line for the security in a mining environment. We focus about the performances on the second one because it's the more complex. So we want to know which are the performances, and to do so we consider a subset of a mine pump in order to know which is the comparison between our approach, the delta-based approach, and the product-based approach. As you can see from this slide, in an original scenario in which we consider three methods, we have that our approach is comparable to the product-based one. But if we consider an evolution scenario, by adding a single feature, by adding just one method to be verified, then we have that our approach is way more efficient because we only have to verify the new delta, define the new method, while the product base has to generate each possible version and it has to generate each possible variant. In this way, we can see that our approach is way more efficient and has way less cost than the product-based one. So, to conclude my talk, I will recap which was the challenge that is overcome Liskov restriction without increasing the cost, so that we are able to change behavior while applying deltas, and our solution is the delta-based verification. So we represent the original calls as abstract statement, and by using a normal form, we are able to locally specify and verify modifications. To do so, we use the abstract execution in order to verify the contract, and also we use abstract execution to prove that the rules, the transformation rules to refactor methods that are not in the normal form but can be refactored in normal form are correct. To evaluate our approach, we consider the expressiveness and the performances. As you can see, our approach is expressive enough to represent, to model widely used case studies in the literature, and also our approach outperforms the product-based one. Thank you for your attention.